Hello everyone. In this video, we will cover normal approximation applied to life insurances. Consider a large group of insureds. Altogether, there are n independent lives at age X. All lives are governed by the same mortality model, and each individual purchased an identical insurance policy with identical benefits. Let Zi be the present value random variable for the ith insurance policy. That is, the expected value of Zi equals to the expected value of Z. They have the same expected values because the policy are identical with identical benefits. And then the variance are the same. Variance of Zi equals the variance of Z. And we are interested in a random variable S, which is the sum of the Z's. This S corresponds to the present value of the aggregate payment over all policies. Therefore, the expected value of S, which is the sum of the expected value of Zi, which equals n times the expected value of Z. Similarly, the variance of S is n times the variance of Z. We will use the normal approximation by the central limit theorem. S is approximately normal with mean ES and variance of S. We are interested in to determine an initial amount of fund, say S, such that the probability that the fund is sufficient to cover all claims is P. That is, we want to get the 100 times P percentile of S. The corresponding notation, the expression is the probability. The random variable S is less than or equals to the value S equals P. P is the probability. We have S equals to Z1 plus Z2 plus up to Zn. Under normal approximation, we can express this as S minus the expected value of S over the square root of variance of S, where the expectation and the variance is given by this. And this is approximately follows a standard normal. All right, so this is the idea. Let's take a look at an example. There are altogether 60 independent life, all at age 40. Purchase a 5-year deferred whole life insurance. The death benefit is 20, payable at the moment of death. Given that the force of mortality, 0.01, force of interest, 0.05. Using the normal approximation to calculate the size of the fund required, such that the probability that the fund is sufficient to pay all benefits is 0.95. All right, the solution. Let Z be the present value random variable for one life. The expected value of Z is 20, the death benefit, and then times the expected value of the 5-year deferred whole life insurance at age 40. And upon calculation, we get the expected value of Z. The second moment, a death benefit of 20. So for this expression, we need to square the death benefit. So we have 20 squared. And then the second moment of the 5-year deferred whole life insurance. For the second moment, we need to square the death benefit. And then we need to change the delta to 2 delta. So here, the first term is the square of the present value factor. do not square the expression for the force of mortality. Remains constant, e to the power minus 0.01 t. This is TPX. Upon calculation, we get the second moment. And then we can get the variance of Z, which is 14.882086. All right, we get the expected value and the variance of Z. And let S be the present value random variable for all 60 life. This corresponds to the aggregate present value. The expected value of S is the number of individual 60 times the expected value of Z, and the variance of S is 60 times the variance of Z. We want to get the probability that the aggregate present value random variable S is less than or equal to S. We need to determine this small s. The probability is 0.95. Convert to standard normal. And the 95th percentile corresponds to a standard value Z 1.64485. So that is, we have this expression equals to 1.64485. We get the expected value of S and the variance of S respectively. Upon calculation, we get the answer. The initial amount of fund is 197.3148. Let's take a look at another example. A group of 200 independent life, all at age 40, each purchases a 25-year term insurance. Death benefit is 150, payable at the end of the year of death. So this is a discrete insurance. Given that Lx is 100 minus x, the benefit payments are to be withdrawn from an investment fund earning an interest rate of 0.05. Use the normal approximation to compute the initial fund balance today so that there is a 90% probability that the fund is sufficient to pay all claims. Let's take a look at the solution. Let Z be the present value random variable for one life. The expected value of Z, we have 150, and then times the 25-year term insurance. All right, the formula for getting the expected value of the N-year term insurance. KPX and QX plus K. Using the life table function Lx, we get 1 over 100 minus x. And x is 40. Substitute into the expression here. Nu is 1 over 1 plus I, which is 1 over 1.05. KPX times QX plus K, 1 over 60. And we get this expression. And then this summation. This summation is 1 over 60. And this corresponds to a 25-year annuity at I equals 0.05. From that, we get the expected value of Z, 35.234861. The second moment, the square of the death benefit amount, 150 square, and then times the second moment of a 25-year term insurance. The expression, the square of the death benefit amount, and then change the delta to 2 delta, which corresponds to nu square. And then the terms 1.05 raised to the power minus 2 times k plus 1, we can rewritten as 1.05 square and then raised to the power minus k plus 1. And this expression, together with the summation, this corresponds to a 25-year annuity at interest rate 0.1025. And therefore, the second moment, we can get this quantity. From this, we can get the variance of Z. All right, and then the aggregate present value random variable. For all 200 lives, the expected value of S equals to 200 times the expected value of Z, and then the variance of S is 200 times the variance of Z. And we want to get the value of S such that the probability of this equals 90%, 0.9. Convert into standard normal. And the 90th percentile correspond to the Z value. The standard normal random variable value is 1.28155. That is, we have S minus the expected value of S over the square root of the variance of S equals to 1.28155. Do the substitution. And then we get the answer. 7,877.1166. All right, that's it for today's video. Thank you for watching and see you in the next video.